Good afternoon, everybody. Welcome to Monday afternoon of Chem 170 with your host, me, Dr. White. Hope you all had a nice Thanksgiving weekend. I did. Oh, did I? Oh, boy, was it good? And I had spent some quality time also with my best friend and his wife. That was good too. So let's get going. All right, important things today. What's the game plan? One, and go through important informations. Two, I'll do the review for test 4. Oops, got to get that fixed. Test 4. Then we'll go through the carbohydrate problem set. And then I'll finish up the day, if we have time, which I think we will, with proteins and amino acids, which will not be on test 4, but some will be on the final. And I'll talk about that coming up later in the week about the final. All right, with the game plan set, let's do it. All right, first of all, important information. As you see on the screen, let me check because now I can check. I don't have to ask. And you should see test number 4, important information. This Wednesday, I will be giving test 4 online. And on Tuesday, you'll be able to download test number 4 PDF file. And then on Wednesday at 4 p.m. or earlier, probably a lot earlier, because we'll just have a short lecture. We're just about done. And the lab, which is real quick. I'll send out an email with the password for test number 4 PDF file. You'll have until Thursday, 11 a.m. to finish test number 4 and upload your answers as a single PDF file to the assignment area D2L. Should take you about 45 minutes to finish it, but hey, we're online and it's Thanksgiving or just after Thanksgiving, so take as long as you need to complete the test. Now, test number 4 will cover polymers, lipids, which is fats, oils, and steroids, and carbohydrates. It has 9 pages, 20 problems. Some of the problems are multiple part. As I mentioned earlier, I have never and will never do a multiple choice in Chem 170, and I won't. And here the point breakdown. 54 points general knowledge, nomenclature 15, reactions 36. It adds up to 105, so there's 5 bonus points. Now, 54 general knowledge? Well, if I ask, is my left hand chiral or achiral? Well, that's not reactions, that's not nomenclature, so it must be general knowledge. And that's why the points are that high. Now, this won't be an open note test. Today, I'll be reviewing test number 4. We'll have our regular Zoom meeting on Wednesday for our lab and other material. Please don't forget the extra credit project is due on, well, it's not due, but the deadline is this Wednesday, the 30th. Remember, this is optional. I hope you all had a great Thanksgiving weekend. I did. Oh, did I? Oh, did I? All right, let me just again remind you, you go to the assignment area. Nope. All right, I can't do that from this view. Hold on one second. And I can do this. And let me remind you that you can't see what hold on. Now you can see it. All right. Now, let me remind you, the extra credit project is 10 10 bonus points. And the way to do that is you need to find 10 molecules, organic molecules, and you can get up to 3 molecules per product of something you could buy and use in your daily life. To get full credit for a molecule, all entries in a row of a chart must be right. Each entry, you need to record the name of the product, the name of the molecule and be common or IUPAC that's in that you're picking from that product, and name one of the functional groups, or if there's only one, name that functional group that's in that molecule. And don't forget to put your name on the chart. Here's an example: product, brand X wine, molecule, ethanol, and the functional group is alcohol. Now, to make this interesting, you can't use the molecule sucrose ethanol, also known as ethyl alcohol, isopropyl alcohol, or 2-propanol, acetone, ethyl acetate, propane, acetic acid, or methane. You can't use the products beer, wine, vegetable oil, vinegar, gasoline, propane gas, natural gas, orange juice, milk, sugar, butter. Everything else is fair game. However, note, ingredients must appear in an ingredients label of the product, and they must contain a functional group we discussed in class, which gives you a lot of choices. But stay away from stuff we haven't. The reason I put that in, students usually when we talk about, they identify a functional group we did not talk about in class, they always get it wrong. So that's to benefit you. Again, it's due by the end of the day on the 30th, and no late. Projects are accepted, uploaded as a PDF or MS Word file. Again, this is optional. You don't have to do it. But if you get it right, it's 10, 10, 5, and 5, 10 extra points. It's like getting 10 more points on one of your tests, which is not bad. All right, as a special service to my students, before the deadline, which is this Wednesday, so today or tomorrow, send me via email your project. I'll look at it. If there's anything wrong, I'll get back to you and let you know you got to fix this, and I'll give you some hints how to do it. And there's no reason you shouldn't be able to get 10 bonus points. And I'm looking, oh, here it is. Here's an example, Carmex. One of the molecules in there is phenol. And you can use, hold on, let me get the label right. You can use this phenol, and there's 2 possible functional groups. One's aromatic or benzene ring, and the other is an alcohol. Now, common mistake students make is, oh, we've got to have every 10 different functional groups. No, all of them could be alcohols, all of them could be double bonds, all of them could be ketones, aldehydes, carboxylic acids, or any combination. And with that, you should really do the extra credit project. Hint, it's 10 bonus points. All right, any questions on that before I move on? All right, let me close something. And everybody should see test 4 review. All right, let's talk about things you should know for test number 4. And I should also mention, so I will, that this file, test number 4 review by me, Dr. White, is located in the lecture section of Blackboard under the secret name, test number 4 review. All right, let's go through it. You should know what a polymer is. A polymer is a macromolecule, that means a big molecule, made up of repeating units called monomers. And monomer is a single unit. Think of a polymer as like a long freight train, where the box cars are the monomers. Now, when we classify polymers, There's two different ways to do that. One's by chemical property, a key one, another by a key physical property. For chemical property, there are two main types, addition polymer and condensation polymer. You should know that a addition polymer is a polymer made with only one type of monomer. Again, an addition polymer is a polymer made with one type of monomer. And examples that you should know are rubber tires or saran wrap, the kitchen plastic wrap. Now, the other type is a condensation polymer. And a condensation polymer is a polymer made with two or more different types, and I should have the word different in here, different types of monomers. An example of that would be the polyester in my plastic water bottle or a plastic pop bottle. Another one would be a nylon jacket or a urethane foam insulation would be an example of a condensation polymer. And you should know a condensation polymer is a polymer made with two or more different types of monomers. And the examples like a plastic water bottle, and you could put down a plastic pop bottle. Remember, I'm from the Chicagoland area. The stuff in a bottle or a can that's carbonated, non-alcoholic, we call pop, not soda. All right, now the other way of classifying polymers is by physical property. And a physical property example, the two types are thermoplastic and thermoset. And you should know a thermoplastic polymer is a polymer once formed, it can be reheated and shaped. And what that means is this plastic water bottle is a thermoplastic. When they made it, they had the polymer and beads. They heated it up to form this shape of the bottle. Now I can cut it up and heat it up again if I was in the right chemical facilities and remelt it and you reshape it into a new bottle or whatever. An example of that would be plastic water bottle. Another one is saran wrap. There's no correlation between addition or condensation polymer with thermoplastic or thermoset. The only way you know whether something's thermoplastic or thermoset, you got to test it. Now, again, thermoplastic polymer, once formed, it can be reheated and reshaped. Examples of this are plastic water bottle and saran wrap. Now, the other example is thermoset polymer. And this is a polymer once formed, it cannot, and that's the important thing, it cannot, that's why I have it underlined, be reheated or reshaped. And what would be an example of that? Car tires, rubber car tires, or any kind of tires. I'll put in for now, rubber car tires. And another one is urethane foam insulation. Once you make it, you can't cut it up, reheat it, and reshape it. And if you've ever seen pictures in strife, what would be the right term? Politically strife areas where people are revolting against something, you'll see a lot of people will put tires in the middle of a road and set them on fire as a blockade. And they do that because they don't know it, but it's a thermoset polymer. The tires don't melt, they just burn. All right, next, I talked about lipids in the fats and oils part of the lipids chapter. And a lipid is a molecule or molecules from plant and living things like you and me or animals or plants, I already have plants, that are soluble in nonpolar solvents, but not water. Now, there are two types of lipids, saponifiable lipids and non-saponifiable lipids. And non-saponifiable lipids yield carboxylate anion of fatty acids, plus also glycerin, but I don't put that, they don't put that in definition, when you react the saponifiable or lipid with base and water, alkaline conditions. And the molecules that are called saponifiable lipids are fats and oils. So fats and oils, you should know, are saponifiable lipids. Now, the other type of lipid is non-saponifiable lipid. They don't react with base and water. And there, I'm talking about the steroids, otherwise known as your hormones. Now, when we talk about a fat or oil, you should know a fat is a solid or semi-solid triglyceride at room temperature. And room temperature, in case you're wondering, is 25 degrees C by definition in science or chemistry at least. And you should know an oil is a liquid triglyceride at room temperature. So this is a fat, solid or semi-solid triglyceride at room temperature, oil, liquid triglyceride at room temperature. Now, the structure of all fats or oils is this triglyceride right here, right there. And notice there's 1, 2, 3 esters. Remember, oil chemists, which are chemists who deal with fats and oils, write their ester this way, as opposed to synthetic organic chemists, and I'm both, so I can write them both this way. Either way, carbonyl, oxygen with an R group, carbonyl directly bonds to an R group. And notice in all triglycerides, there's not 1, not 2, but 3 esters. So what's the key ester in a fat and oil? What's the key ester? What's the key functional group in a fat and oil? An ester. Now, just like you learned for test number 3, key reactions that we'll go over for fats and oils, you've already learned for esters. If I take an ester and react with acid and water, acid hydrolysis of an ester, you get back the alcohol and the carboxylic acid you would have used to make that ester. Well, if you look at this triglyceride, 3 esters, this alcohol, this ester gives this alcohol plus this carboxylic acid. This ester gives this alcohol plus this carboxylic acid. And this final ester gives this alcohol plus this carboxylic acid. And this triol, 3 hydroxyl groups, which I won't ask on a test, but we've talked about, is called glycerin. And these are fatty acids I'll talk about in a little while. If we have an ester and react it with base and water, sodium hydroxide, this is called saponification of an ester. You have, not saponification, saponification of an ester. And here, you get back the alcohol you would have used to make that ester, but in the presence of base, the carboxylic acid forms the carboxylate anion. Again, base, carboxylic acid, you get the carboxylate anion. If you take a fat or oil, this triglyceride, ester 1 gives this alcohol plus this carboxylate anion. Ester 2 gives this ester plus this carboxylate anion. Ester 3 gives this alcohol plus this carboxylate anion. Now, I showed you an important reaction, which I work for a company. We use this to the tune of about 2 to 3 million pounds. We would react every week of fats, and we didn't deal with oils because the fats were cheaper. That is, if you take an ester and react it with steam. Steam is very, very hot water, especially high pressure steam. It can kill people. It's that high temperature, really damage your body quickly. And here, as I mentioned when we went over this, there's two ways to make a reaction go quicker, easily. One is use a catalyst like acid or base. Another way is to increase the reaction temperature. So if you use hot water, steam, you do that. And this gives you back the same reaction products as acid hydrolysis of an ester. You take the ester, do steam hydrolysis, you get back the alcohol you would have used to make that ester, plus the alcohol, the carboxylic acid you would have used to make that ester. So if we take our fat or oil, steam, which is hot water, first ester gives this alcohol, this carboxylic acid. Second ester gives me this alcohol and this carboxylic acid. And the third ester gives me this alcohol plus this carboxylic acid. In other words, glycerin plus these fatty acids. Now, fatty acids are carboxylic acids, and organic chemists are lazy. They don't want to say carboxylic acids derived from fats and oils. They just say, let's call it a fatty acid. And they do. And I've asked you to learn, if I put down, draw the structure of stearic acid, here's this fatty acid, 18 carbons, CH2 is repeated 16 times. Or if I put this molecule on its S, what's its common name? Stearic acid. I also asked you to learn oleic acid. Oleic acid is a unsaturated fatty acid which has at least one double bond. In this case, it does. And this is at C9. And here we have a carboxylic acid, 7 CH2s are double bond, 7 CH2s and CH3. And it has 18 carbons like stearic, but it has a double bond at C9. And on a test 4 or the final exam, if I ask, give the structure of oleic acid, you should know how to draw it. If I put that structure down, you should know. If I ask, give the name, common or IUPAC name, and nobody calls this by the IUPAC name, even though I do know it, I wouldn't. It's oleic acid. Now, a couple definitions you should know. Saturated fatty acid is a fatty acid, a saturated fat, I should say, is a fat that only has carbon-carbon single bonds. Now, if you only put down carbon-carbon, if you only put down single bonds, I'll mark it wrong because there's a carbonyl in fats, which is a double bond. But saturated fat has only carbon-carbon single bonds. Unsaturated fat has at least one carbon-carbon double bond. Now, since I worked in this industry for a number of years, I asked you to learn some common names of different types of fats. And one you should know, tallow is beef fat, yellow grease is pig's fat, and white grease is another type of pig's fat. The difference between, which I'll never ask on test, between yellow grease and white grease is their color and their price. But for most things, like a company I worked for, all three of those were interchangeable. The yellow grease and white grease were the cheaper. So if we could get it, we would. Because if you're buying 150 million pounds and you can save 2 cents a pound, that's a lot of money. And it is, and it was. All right, now, to give you a real life feel for fats and oils industry, because I worked in there, I came up with a general structure for tallow, yellow grease, and white grease. And That's this right here, where this R group on the carbonyl is the sterol R sub S. On the second ester, this carbonyl R sub O, oleal, and the third one, same thing. And it's essentially a 50-50 mixture. Well, how can you do 50-50 when three things? We can't. So, and also my joke, SOS, save our ship, help. And therefore, if I ask if you take tallow, react with sodium hydroxide and water, what are the three different products you get? And remember, what's the functional group in tallow, white grease, yellow grease, and ester? And here you have sodium hydroxide and water, and just like we did earlier, you get back the alcohol plus the carboxylate anion of the carboxylic acid you would get from this ester. So ester 1, we get this alcohol plus this carboxylate anion, sodium stearate. Ester 2, we get this alcohol plus this carboxylate anion, sodium oleate. And the third one, we'll get this alcohol. But since we don't balance equations in my class, in Chem 170, you don't need to. You get sodium stearate again. If you wanted to put a 2 in front of that, you can, you don't. But notice there's 1, 2, 3 different products from that reaction. And you should also know the reaction of acid and base, or with base and water and with steam, with tallow, yellow grease, and white grease. And we'll go through some of that. Well, we did go through that when I went through the fatty acids or the lipids, otherwise known as fats and oils problem set. Now, one of the most important things I can teach you this semester is how does soap work? Hold on. Everything you should know in this review, but this one, really know. And how does soap work? You should know the structure of soap is a non-polar tail, polar head. And the key to the puzzle is like dissolves like. What I don't have up here, I should. And you should know water is polar, dirt and grease are non-polar. And like I said, like dissolves like is the key to the puzzle. And that is things that are polar are soluble in polar things, things that are non-polar are soluble in non-polar. When you try to mix two together, they're not soluble, which is why water doesn't get dirt off your hands. But when you use a soap, and this is all stuff you should know, because of like dissolves like, the non-polar tail of soap is attracted to dirt, if this were a little dirt particle on your hand, and the polar head of soap wants to stay all the way far away. I've only shown a few, but it covers the whole dirt molecule, and you should know this is now called a micelle. And because the micelle is covered, the dirt, and all you see are the outside polar heads, the micelle looks polar to water, and the water says to the micelle, I know like dissolves like, and you do. You look polar, so I'm polar, you're polar. Let's go down the drain together. And they do. Now, steroids, you should know how to draw the ring skeleton for a steroid. And let's see if I'm having a good ring drawing day. You have a 6-membered ring. Next to it, another 6-membered ring. Up here at 12 o'clock, another 6-membered ring, and then next door, a 5-membered ring. 1, 2, 3, 4 rings. And they're like that. And if I ask on test number 4 or the final even, draw the ring skeleton for a steroid, you should know how to do that. All right, next we talk about carbohydrates. And you should know what's the definition of a carbohydrate. That's a polyhydroxyaldehyde. Remember, poly means many. Hydroxyl OH group, aldehyde, carbonyl with R and H, or a polyhydroxy ketone, or molecule upon hydrolysis, meaning adding water and maybe a catalyst, becomes a polyhydroxyl aldehyde or ketone. Next, I talked about chirality. And you should know chirality is Greek for handedness. Actually, I found that out a couple of years ago. It was interesting. I had 2 students, not 1, but 2 in my Chem 170 class who were fluent in the Greek language. And they confirmed chirality means handedness. Aren't you glad they didn't pick the word footedness for that? Well, anyways, and you should know what is a achiral object and what's a chiral object. And an achiral, A means without handedness, chiral, object is an object with a superimposable mirror image. And later today, we'll go through the carbohydrates problem set. We'll practice this. And you should know a chiral object is an object with a non-superimposable mirror image. Oh, don't tell anybody. Shh. But if you see the name right or left in a description of an object, it's always going to be chiral. Like, is my left hand chiral or achiral? Well, the left tells it away. Same thing as my left foot or my left ear, chiral or achiral. Bet you didn't think about your ears being chiral or not. Well, they are. Think about it. Well, I'll tell you. Oh, since we're not face to face, and I have up here above my monitor 2 huge powered amplified speakers, I don't need to wear my hearing aids. Unfortunately, in my family, bad hearing is hereditary. My grandfather on my mother's side had it. My mother had it. Oh, she had bad. And my sisters have it. And guess what? So do I. I've got about a 60% hearing loss. But you have hearing aids, it helps. And it's interesting, the hearing aids are chiral because your ears are chiral. The right hearing aid doesn't fit in the left ear. The left hearing aid doesn't fit in the right ear. But you never thought the insides of your ears are chiral. They are. Here, let me get a mirror. Can you see this non-superimposable with this side? Uh-oh, it's Awful Humor Monday sneaking out again. All right, now, next, since we're talking about chemistry, organic chemistry, the most important thing is the carbon atom. Let's talk about chiral carbon atoms. And you should know that a chiral carbon is a carbon atom with 4 different groups, 4 different atoms, or a combination of 4 different groups and atoms. If it has more than 2 of the same atom or group on it, it's not a chiral carbon. Next, I talked about enantiomers. Enantiomers are non-superimposable mirror image. Now, we talked about glucose being a sugar, and that's a mono and disaccharide, and I'll never ask you what's a sugar on a test, but since I used that, I better tell you what that means. An important reaction you should know is the reaction of glucose with itself to form a hemiacetal. And for test number 2, you learned aldehyde or ketone, alcohol acid catalyst forms a hemiacetal or hemiketal, depending on what R prime is. Now, in glucose, you have an aldehyde at the top, alcohol at C5, carbon number 5, and because it's in the same molecule, it's called the intramolecular reaction, and you don't need a catalyst, but you do have, instead of a one-way reaction, this equilibrium. And this reacts and attacks just like here, and here was my carbonyl carbon, and it now has the bond to this oxygen, OR, this carbon is the R, and you have HOH on there, and then here's my R prime and R double prime. R prime is hydrogen. On a test, I give you the structure for glucose and double arrows. You should know how to draw this product. On test 4, if I give you this product and say what's the starting material, you should know it's glucose or draw glucose. Same thing for fructose. By the way, glucose is called has an aldehyde. Fructose, the sweetest sugar, has a ketone. This carbonyl reacts with this alcohol, same reaction, to form a hemiketal, and everything else doesn't change. I should mention now, your friends on every test in the final, do you break carbon-carbon single bonds? No, you don't. And how many bonds to carbon? Oh, I gotta get to 6 someday. 4. Let's see. Nope, it's still broken. I said it was Bad Humor Monday. 4 bonds to carbon. Remember that. Also do the practice problems. So on a test, you should know if I have a ketone or aldehyde, or in this case, fructose. If I put this structure down, you should know how to draw this product. If I put this down as a product with the double equilibrium, you should know how to draw fructose or write the name fructose down. Now, important reaction, which is a slight change from what I taught you for test number 2. You take this hemiacetal or hemiketal reactor with an alcohol and acid, you'll get this acetal or ketal. So if you start out with the hemiacetal of fructose reacted with an alcohol acid catalyst, you'll get this acetal. OH is replaced with OR triple prime. What's the reason this is important? Because that's how Mother Nature makes complex carbohydrates, like starches. Now, things you should know about sugars and carbohydrates. Fructose is glucose of that. Let me say it, start again. Sucrose is fructose plus glucose bond together. Sucrose, table sugar. Starch is a lot of glucose molecules linked together, polyglucose. So what that means is you take a lot of glucose and add some acid catalyst, otherwise known as an enzyme, you'll get starch. And remember, what's the key functional group in a carbohydrate? And that is an acetal linkage. So what that means is you take sucrose and water and acid, like in your stomach, you'll get back, just like acid hydrolysis of an acetal, ketal, you'll get back fructose and glucose. If you take starch and acid and water, just like in your stomach, you'll get glucose back, which is why glucose is the most abundant sugar in nature. We make it in our body by breaking down starch with the acid and water in your stomach. And it's the most common, it's the sugar in our blood. Now, leaving my class, you should know how to describe with words and a chemical reaction, a general chemical reaction, what happens in your stomach when you eat a fat or oil in your stomach. And I can get personal now. I think this is one of the miracles of life that you and I have in our stomach cells that make hydrochloric acid, otherwise known as the fancy word synthesized hydrochloric acid. How it does that, I've never looked it up. That's in organic chemistry, but it's important. And you have hydrochloric acid, and you've been drinking your water. Speaking of, and the water and acid on your stomach, if you chew your food and swallow it, otherwise you'll choke. And my mother taught me that when I was 2. I found out she wasn't lying. I did choke one time. I learned after that, always chew your food before you swallow. Goes into your stomach. And you should know the general reaction. First of all, how do you describe what happens in your stomach when you eat a fat or oil? Acid hydrolysis in a key functional group of fat or oil of an ester. And the general reaction you learned for test 3 is ester, acid, water, get back the carboxylic acid and the alcohol you would have used to make that ester. Next, eat a carbohydrate. When you chew something like if you had bread for lunch or French fries or potato chips, things I don't need. But anyways, good stuff. But ask what's in your stomach, acid and water. So it's acid hydrolysis. What's the key functional group in a carbohydrate like starch or sucrose? And acetal. And you learn for test 2, acetal or ketal, acid and water. You get back the aldehyde or ketone you would have used to make that acetal or ketal plus the alcohol. We don't balance it, but if you wanted to put a 2 there, can I do that any smaller? I'll have to try. And that's that. So you should know the things I just talked about for test 4. Remember, test 4, I'll be sending out the password this Wednesday. You'll have till Thursday to finish it. And if I look at the clock, this would be a good time to take a break instead of going into our break time and rushing. And after the break, I will do the ketones and aldehydes problem set. And so come back in about 5 minutes, 1:50, and we'll continue. I'll see you in 5. I can get up and stretch. Oh, sorry about the delay. I went and got my mail. I was reading some of it. I'm sorry. All right, let's get going. All right, I promise I go through the problem set for carbohydrates. So let's do it. All right, let's go through the problem set, which you should see on your screen right now. And the first question is, you should know, what's a carbohydrate? Oh, I apologize. Getting near the end of the semester, Dr. White gets lazy. C knows. What's a carbohydrate? It's a polyhydroxyaldehyde or a polyhydroxy ketone, or a molecule upon hydrolysis becomes a polyhydroxyaldehyde or ketone. And next are the following items: chiral or achiral. Achiral, superimposable mirror image; chiral, non-superimposable mirror image. If you see the name left or right in the name of an object, it's always going to be chiral. So my left foot is chiral. Now, mitten with no leather palm, if you draw the mirror image, they're superimposable. Well, your hands aren't, but the mittens are, and therefore it's achiral. Tube socks. Well, if there's no toes, I should have also put on there design or writing on it. It's got a superimposable mirror image. It's achiral. And if you remember, I did that great artwork. Sewing needle has a superimposable mirror image. So does a piece of rice. So they're both achiral. Now, something you may not be familiar with, you've never played baseball. I remember the first one my father got for me, baseball glove. A baseball glove is like your winter gloves. There's one if you use it on your left hand and the other on the right hand. And just like your winter gloves, if they're not mittens, they don't fit on either hand. And I remember when I got my first baseball gloves, since I'm right-handed dominant, even though I'm ambidextrous, my father got me, we went out and bought it. Oh, it's a nice memory. My left-handed baseball glove. So it's chiral. Your face, remember we did in class, touch your right ear. Dr. White says, how do you know you're right from your left? Because your face is chiral. And finally, remember did I do a car? I think I did the car. Car, it has a non-superimposable mirror image, therefore it's chiral. And if you were standing in front of a car and someone said, you get in on the left side, how would you know which side it is? Because it's chiral. There's left from right. Next, circle the chiral carbons in the following molecules. Now, as I taught you in lecture, if a carbon has two or more of the same atom or group, it's out. Therefore, this CH3 is out, this CH2, this CH3 is out, two or more hydrogens. Now, this one has a chlorine, hydrogen, methyl, and these three carbons with the chlorine hydroxyl. So it's chiral. This carbon has chlorine, hydroxyl group, methyl, three carbons with a chlorine, four different groups on it, or atoms, or combination of which this is. So that would be circle chiral. Now, if a carbon is in a double or triple bond, it can't be chiral because you need four different groups. It can't have four different groups if it's in a double or triple bond. So immediately these two carbons are out. Two hydrogens on that carbon out, three hydrogens out, because you need four different groups. As long as you have two or more of the same atoms attached to a carbon, it can never be chiral carbon. So that leaves this one to look at. Hydrogen, thiol, SH, methyl. This is called allylic, three carbons with a double bond, four different groups or atoms. It's chiral. Now, if we look at the next C, this carbon in the ring is attached double bond to oxygen, carbonyl, so it can't be. Remember, there are 4 bonds to carbon. So this carbon has 2 hydrogens. This one has 2. This one has 2. So it's out. This carbon on the ethyl group has 2 hydrogens, and here 3 on the end carbon of the ethyl group. So these are out. And the only carbon left is this one, hydrogen ethyl group. These 2 carbons are, these 2 carbons with the carbonyl are prime. 4 different groups or atoms or combination, and therefore chiral. And the same thing here, CH2, CH2, CH2. This has 4 different groups, hydrogen, hydroxyl, these 2 carbons plus these 4 carbons. And the CH3 here has 3 hydrogens, so that's out. And this carbon has methyl, hydrogen, these 2 carbons, and these 1, 2, 3 carbons with the hydroxyl group. 4 different groups or atoms or groups. And if we look at these, remember, in a Fisher projection, each intersection of a line is a carbon. Here we have an aldehyde, remember, a carbon, double bond to oxygen, so the carbonyl carbon is out. This carbon, guess what? 2 hydrogens, that's out. But each one of these would have 4 different combination of group or atom, and they're all chiral, same thing in F. And hold on 1 second, I gotta scratch my ear, excuse me. Sorry about that. And here it says, draw the enantiomer of the following molecule. What that really means is draw its mirror image. I like putting in my mirror. You don't have to dot a line. What's closest to the mirror, you'll see first. What's farthest away, you'll see farthest away in the reflection. Now, achiral carbons, you don't have to do that, top and bottom. And here, hydrox group is closest. You'll see that on this side, hydrogen is farthest away. And same thing through the next. Now, I should have, and I forgot to take out B, just cross that off. I will never put that on a test or final. And you've got my word on that. Plus, it's on the video. So you got proof there. I don't do that. All right, same thing here. C, no, not same thing. C, enantiomer mirror image. Notice bromine on this carbon is closest. Hydrogen is farthest away. I gave you another one just for good measure. Now, here's the structure of fructose and glucose. I'll never ask on a test, what's the structure, but you should be familiar with it. And notice for the following reaction, I won't give the structures of fructose and glucose, but you can name the products if you don't want to draw them. All right, A, glucose and fructose acid, what you get comes together to make sucrose, table sugar. A lot of glucose reacting with a lot of glucose, acid catalyst, you will get starch. Now, here, this is an old one before I perfected how to draw this more in a curved line. You have the hemi acetal of a glucose-like molecule reacting with an alcohol, acid catalyst, hemiacetal acid catalyst, the OH group is replaced by OR triple prime. Everything else stays the same. Same thing here, different R group, benzene ring. Now, remember, in your stomach, you have acid and water, and sucrose is fructose and glucose bond together in a hemiacetal reaction. And here we have, or I should say, acetal. And here we have acetal or ketal, acid and water, get back to aldehyde or ketone, and the alcohol you would have used to make that. Now, in glucose and fructose, they're in the same molecule, aldehyde, ketone, and alcohol. So here it's glucose and fructose held together, breaks apart to make glucose and fructose. Starch is a lot of glucose molecules held together by acetal linkage. When you do this reaction, you break it apart and you get back glucose. Now, G, cross off. Amylose is just another starch, which I haven't asked you to learn. And that's the problem set. Now, once again, I would like to repeat you should know when you eat a fat or oil, how to describe with a general reaction what happens in your stomach when you eat a fat or oil, and that is acid, acid hydrolysis of, and what's the functional group in an acid of fat or oil? That's an ester. And what's the general reaction of acid hydrolysis of an ester? Ester. Acid, water. You get back the carboxylic acid you would have used to make that ester, plus the alcohol you would have used. Hold on, let me make a better oxygen. That's better. And you get back the alcohol you get. So when you eat a fat or oil, you should know, leaving my class, hint that how do you describe with words and a general reaction what happens when you eat a fat or oil? That's acid hydrolysis of an ester. You should also know how to draw that. And here we have an ester, acid, water. You get back the carboxylic acid plus the alcohol you would have used to make that ester. You should also know when you eat a carbohydrate, how to describe with words and a general reaction what happens in your stomach. Well, in your stomach, there's acid and water, and we call that acid hydrolysis. And what's the key functional group holding glucose together in carbohydrates? An acetal. And you should know that. Hint. And how do you draw the general reaction of acid hydrolysis of an acetal? Acetal or ketal. When R prime is hydrogen, it's an acetal. When it's carbon, it's a ketal. Acid, water. Keep your eye on the carbon with two oxygens. Becomes this carbonyl, carbon double bond to the oxygen. So you get either this ketone or aldehyde. If R prime is hydrogen, it's an aldehyde. If it's the carbon's ketone, plus you get back the alcohol you would have used to make that. For those of you who must, I think it's about as small as I can put it to, but you don't have to. You don't have to put it to. Wow, that's a lot of twos. I said it was evolving into Bad Humor Monday, and it has. So you should know, leaving my class, when you eat a fat or oil, how do you describe with words and a general reaction what happens in your stomach? Key functional group in a fat or oil is an ester. That's acid hydrolysis of an ester. And here's the general reaction. Ester, acid, water, get back to carboxylic acid plus the alcohol you would have used to make that ester. What happens in your stomach when you eat a carbohydrate? You should know how to describe with words and a general reaction what happens. What's the key functional group in a carbohydrate holding glucose together? And that is an acetal. I like those special effects, holding glucose together. I said it was bad humor one Monday, and it is. Usually I say that till Wednesday, but not this week. And the key functional group holding glucose together in a carbohydrate is the acetal. So in your stomach, acid water, it's acid hydrolysis of an acetal. And here's the general reaction. Acetal, ketal, acid, and water. You get back to the alcohol or aldehyde you would have used to make that acetal plus the alcohol. Now, let me review two reactions you should know. This is glucose. And this equilibrium, what's the product or products of this reaction? It can react with itself inside of itself. And the key reaction here is if it was intermolecular between different molecules, you need an acid catalyst. Since this is in the same molecule, intramolecular, you don't need it, but keep your eye on the carbonyl carbon. That's where all the fun is. What is attached to it stays attached, and you form the semi-acetal or hemiketal. Now, here's our carbonyl carbon. Let me rewrite it. I'll leave it like it is. And this carbon, C5, this is the alcohol right here. And this attacks that to bond, so this does the same thing. Now, what's not involved in the reaction, I can just redraw because you don't break these bonds. This carbonyl, which is this, opens up to this, which has a hydrogen hydroxyl group. And this bond here, when you have this reaction, will now draw it this way. And that's the product you get. And you should know this. Now I'm going to put the carbonyl carbon as normally you'd see that like this on a Fisher projection. But to help you out right now, I'll do it this way. And the question is, what would be the product or products for the following. Now, what I've just drawn, let me get this hydrogen on there. This is fructose, the sweetest sugar. And what happens? Well, the same reaction. Aldehyde or ketone plus the alcohol as the catalyst. If it was intermolecular between two different molecules, keep your eye on the carbonyl carbon. What's attached to it stays attached to it. And it opens up to this hemiketal. And again, we have a carbonyl, and the alcohol carbon is on C5. Start top 1, 2, 1, 2, 3, 4, 5. And the same reaction, similar. This attacks that carbonyl. This attacks that one. What's not involved in the chemical reaction stays the same. I'm starting to draw the structure of the wrong sugar. Now, this carbon right here becomes this carbon, and it has OH on there, and then this OR, which comes from this carbon, which you see reacting in the red here. And therefore, you form a bond here. And this you should know. If I give you this structure, you should know how to get to this. If I give you the product, you should know, just like the previous one, you should also know you get fructose. And you can either draw it or write the name. Any questions? All right. Well, in that case, it's time to move on to new stuff. This new stuff will not be on test 4, but some points will be on the final exam. Wow, semester's almost over. We've got next week and then the finals. Let me a quick public service announcement from your host, me, Dr. White. It's important you either come to class next week or watch the videos, because next Monday and Wednesday, I will start, and I'll do a whole semester review. And the reason I do that is it helps my students, which you are, do good on my final. And they do. Now, everybody take a deep breath. Let it out. Take a deep breath. Let it out. All right, my final is the same equivalent to like 2 hourly exams. Relax. And it'll be, I'll put by next Monday, I'll have posted on D2L the specifics, but approximately it's 18 pages. Relax, and it's 210 points. Relax, there's going to be 10 bonus points. Don't tell anybody, I'm being nice. And historically, usually students, the average is about 170 to 180. What? Well, think about that. That means the average is about 85 to 90 on my final, which if you think about it, that's pretty amazing. I'm always amazed. And that happens both online and when I've taught all these years face to face. And part of how I'm able to do that is, one, I've been blessed, thank you, with very good students. And two, I do my review. So make sure next week, show up or watch the video. Oh, I got to open a file. Hold on. First, I'm going to close some files. All right, you should see on your screen, Chapter 17, Amino Acids, Peptides, and Proteins. It's new chapter time, new stuff time. Yay! All right, let's talk about amino acids, peptides, and protein. What's an amino acid? Now, organic chemists are lazy, and the molecule we call an organic amino acid is an organic compound that contains both an amino group and a carboxylic acid. Its real name should be an amino carboxylic acid. That's a lot to say. Let's just call it amino acids. And protein chemists did that. Now, here I have one structure. A better way of thinking of it would be like this. And it's the same structure. And this is an amino acid. They're the same. And notice here, I have my amino group, an amine. And here, with this carbon here, I have my carboxylic acid group. Now, interesting, remember I taught you in ketones and aldehyde. I have a carbonyl here. The carbon bonded to it is called the alpha carbon. And in amino acids, listen carefully. The amino group is always on the alpha carbon. The carbon bonded to the carbonyl group of the carboxylic acid. All amino groups are all amino acids have the amino group on the alpha carbon. Now, what did I teach you just recently about chirality of a chiral carbon? It has 4 different groups, 4 different atoms, or a combination of 4 different groups and atoms. And the alpha carbon of an amino acid, if it's bonded to 4 different groups, you should know this. When R is not hydrogen, it can be anything else. When it's hydrogen, it's glycine, but everything but glycine, the alpha carbon is chiral. Therefore, most amino acids are chiral, which means they exist in 2 forms, an enantiomeric form, right and left, mirror images that are non-superimposable. By the way, that plays an important role in our RNA and DNA. So let's go through this again. I'll write it down here. When R is not hydrogen, when it is, that's called glycine. When R is anything but hydrogen, the alpha carbon is chiral. And that means you can have enantiomeric pairs of amino acids, many of them. Now, click switches in the off position. Now, it turns out amino acids contain both a amino group, which is a base, and a carboxylic acid group, which is an acid. And depending on the pH, if you're close to 7, this acidic proton reacts with this base. We learned it for test number 3, 3, to form this molecule, a salt. Now, notice in this molecule, you have both an anion on this oxygen and a cation plus charge on the nitrogen. And that has a name. Again, switches click off, and those are called zwitterions. And a zwitterion is a molecule that has both a positive charge on one atom and negative charge on another, but has no, in the same molecule, but no net charge. Now, because Dr. White learned German in high school and college, Dr. White's story first. I don't know if they still do it, but when I got my PhD at Michigan State in chemistry, one of the prerequisites or requisites you have to do to get your PhD is you have to pass a language proficiency test. And for me, I took German. What was that test? Well, you had to bring in 25 pages of translated German from a German publication, chemical publication, and you could only have, I think, 10 mistakes. And you brought your translation and a photocopy of the journal. And I think I used Angewandte Chemie, German chemistry journal, I think, or I picked organic molecules publication. And the little old lady who ran this, I didn't listen to my research group, bad Dr. White. And I was told when you go to the other part of the test is you have to bring in 10 pages of a journal articles in the language you were translating, German, and you could only have 5 mistakes, and you had an hour or 2 hours to do all 10 pages. Well, I was warned when you go in there, and this is back a long time ago when everybody wore blue jeans and t-shirts and everything, wear a coat and tie. I didn't, and she failed me. And about 2 months later, I brought in some more pages in another journal article, but this time I wore a coat and tie and made sure I was all looking nice and well and groomed. And guess what? I passed. So it always pays proper image. But anyways, since I know German, Zwitterion gets its name from the German number 2, Zwei, Z-W-E-I. In German, the W is pronounced like a V. And when I used to work in Germany, and I did, either I'd be called Dr. Weiss, which is white in German, or Dr. Veit, which they took the W from the word white and made it sound like they make their W's. So that's why I'm never, let's say I got to think about it. If I look at this, Americans would pronounce it, I got to think about it again. Zwitterion, it's Zwitterion, which is in German. That's an important thing. Again, switches off. All right, switches on. Amino acids can react with each other. And notice I went technicolor. And you learned this general reaction. Carboxylic acid plus an amine can be hydrogen, and what you get is an amide. Well, here, one of the hydrogens is R prime, and this whole group is R double prime. And notice you form the amide. Now, interesting thing, on this end of the molecule, you have more carboxylic acids, which can react with more amino acids. On this side, you have an amine, which can react, well, I said amino acids, the amine part, and this part can react with more amino acids, the carboxylic acid. So you can add on more amino acids. Now, switches off, click. Here we have what's called a peptide bond. The reason I'm going over this, you might need it for other classes you're taking. And that's the covalent bond between the carboxylic acid, called the carboxyl group of the amino acid, with the amino group of another. And this is called a peptide bond, but Dr. White, being not a protein chemist, but a synthetic organic chemist, calls that an amide bond. So the bond here, I call in red amide. But if you're a protein chemist or work with proteins, that's called a peptide bond. And I'll never ask that on tests or my final. This won't be on a test. This will be on the final stuff I'm covering this chapter now. So peptide bond is when you make that amide bond between two amino acids. Now, switches off. Protein chemists, which I've never worked in this area, not that there's anything wrong. This in my career, I never did work in this area. I've worked in many other areas, but not this, is a molecule containing two or more amino acids, which the amino acids are joined together in an amide bond. And that's called a peptide. And again, click, switches off. Now, switch is still off. A protein, like your skin, are peptides in which at least 50 amino acids are bonded together in what they call peptide bonds, Dr. White calls amide bonds. And therefore, whenever you eat anything with protein in it, if you're a vegan, like soybeans have proteins in it. If you like hot dogs, steaks, and other things, ribs, the protein are peptides in which they have 50 or more amino acids bond together by amide bonds, which protein chemists call peptide bonds. Now, switches on. You should know what happens when you digest a protein. You ate something with protein in it, like if you had, I don't know, a good piece of salami for lunch in a sandwich, or now I'm getting really nasty, a corned beef sandwich. Dr. White loves corned beef and pastrami sandwiches. Get from a good Jewish deli. If you've never been to either Kaufman's in Skokie or, what's the name of it? Got a mental break. There's Manny's in Chicago on the south side for a corned beef sandwich. Boy, are you missing out on the great things in life. You should put that on your to-do list. But anyways, when you consume a protein, your stomach and I think small or large intestine, I forgot which, breaks down the amino acid, the proteins to amino acids by acid hydrolysis of the amide, the peptide bond. And you learn for test number 3, you have an amide, and here you have your amide, R prime and R double prime can be hydrogen, one or both. And because we're in our stomach, your stomach has cells that synthesize, that's the fancy word for making, hydrochloric acid and there's water in your stomach, just like the water I just drank, and what you get back is the carboxylic acid you would have used to make that amide, but in the process, you make the amine, but the amines are bases, and the presence of acid, you form the amine salt, which we talked about in test number 2 material. So this is a general reaction, how you break down protein, because the bond holding amino acids together, RA, is an amide. And here's 2 amino acids. I could have put more. Here's our amide. Can be hydrogen. And we add acid, HCl, that's what's in your stomach, water's in your stomach, and you get back the carboxylic acid plus the amine salt of the amine you would have used to make that amide. And here's our amide in the protein. If there are a lot more amino acids linked together, each one undergoes the same. And you get back the carboxylic acid plus the amine salt. Now, interesting enough, this amino group in the acid in your stomach becomes an amine salt. And look what Mother Nature has done. Due to the acidic nature of your stomach and intestine, the amino acids are converted into amine salts, which makes them more water soluble, which helps get them into your blood. Isn't that amazing? So we're done for this chapter. There's not much in it because we've already learned all the chemistry. Now, I want to go back to our whiteboard. This will not be on the quiz number 4, but you should know for the final exam, when you eat a protein, how do you describe with words and a general reaction what happens in your stomach? Well, there's acid and water, so it's acid hydrolysis. And what's the key functional group holding amino acids together in a protein? Remember, I'm an organic chemist, not a protein chemist. Not that there's anything wrong with protein chemists, but it's an amide. So we have acid hydrolysis of an amide. And for test 3, you learn can be hydrogen amide. And the general reaction in amide, acid, and you're in your stomach, I'll call it HCl, which it is, and water, you get back the carboxylic acid plus the amine salt of the amine you would have used to make that amide. So, how do you describe with words and a general reaction what happens in your stomach when you eat a protein? The key functional group in a protein holding amino acids together is an amide. And therefore, we have acid hydrolysis of an amide. That's how you describe what happens in your stomach when you eat a protein with words. The general reaction you should know, again, this is not for test 4, this will be for the final, but you should know this. Amide, acid, and water, you get back the carboxylic acid plus the amine salt you would have used to make that amide. All right. Now, one of the things I mentioned earlier that I can do, because we're face-to-face, not face-to-face, if we were face-to-face, every lab day, I would have only had 50 minutes lecture, and then we'd have to go to the lab and do our lab. But since we were doing our lab online, the way I did it this semester, don't tell anybody, but I stole a lot of extra time to help you practice when we were online, which means I spent more time than I could have normally face to face. What that really means is we're ahead of ourselves, we're ahead of schedule. With that, I'm done for today because we're caught up. We've covered all the material. Wednesday, I'll go through the last lab, and I'll have some important things to talk about, including a few things that are things you should learn about that you can use in your daily life once you know organic chemistry like I do, like how to clean a bathtub, how to get your sink on or in the kitchen or in your tub or in your bathroom unclogged or bathtub unclogged. And I'll go through that on Wednesday. But with that, I'm done for today. So I'm going to say, gang gesund, goodbye now. Don't forget about the deadline for the extra credit project. Don't forget Wednesday, I'll be after class, you'll be doing test number 4. And with that, I'm done. Gang gesund. Goodbye. Bye, Andrew.